Good day, everyone. My name is John Lassin Takao Jr., and on behalf of our team, I am pleased to present our analysis of example 2.7 from the control system course. Today, we will be examining a transfer function problem and identify two key concepts. One is the identification of right half plane zeros and calculation of a step response using the Laplace transform. And the problem is in two folds. One, we need to prove that the system transfer function has zero in the right half. And then we need to obtain the time domain response, that is YT, when the input is a unit step function.
Hi, I'm Miriam, and today we have organized our presentation into different sections with each member covering a specific aspect of the solution. So as you can see from our roadmap, we'll begin with the system block diagram, derive the transfer function algebraically, identify zeros and poles, and then work through the step response calculation using partial fraction decomposition and inverse Laplace transforms. Now I'll hand over to Mesinda, who will introduce the system block diagram.
Thank you. I'm Mesinda Edu, and I'll walk you through the algebraic derivation of our transfer function. So we are going to start with the parallel configuration that we just saw. That is y of s over x of s is equal to 6 over s plus 2 minus 4 over s plus 1. So we need to find a common denominator to combine these fractions. First of all, the common denominator is the product of both individual denominators. So our denominators currently are s plus 2 in one bracket and s plus 1 in another bracket. So the next step we are going to be doing is to expand each numerator by multiplying them by the missing factor. So the first term becomes 6 times s plus 1 in the numerator, and the second term becomes 4 times s plus 2 in the numerator as well. So this gives us 6 into bracket s plus 1 minus 4 into bracket s plus 2 all over s plus 2 in one bracket times s plus 1 in another bracket. So in expanding the numerators, we have 6s plus 6 minus 4s minus 8. We then move on to the next step, which is to now simplify the numerator. So in simplifying the numerator, we have 6 minus 4s giving us 2s and 6 minus 8 giving us negative 2. So our numerator now becomes 2s minus 2, which we then can factor 2 out, giving us s minus 1, times 2. So it becomes 2 into bracket s minus 1. So our final simplified transfer function now becomes y of s over x of s, which is equal to 2 into bracket s minus 1 divided by s plus 1 in one bracket and s plus 2 in another bracket. So this is the factored form, which makes it very easy to identify the zeros and the poles, which my next colleague would be doing for us. Thank you.
Thank you. My name is Umar, and I'll prove that this system has a zero in the right half S-plane. Looking at our transfer function ys over x of s equals to s minus 1 over s plus 1 multiplying s plus 2. To find the zeros of the function, we set the numerator equal to 0 and solve for s. So the numerator is 2s minus 1. Setting this equal to 0, you get 2s minus 1 equals to 0. Therefore, s equals to positive 1. This is our 0 location, s equals to positive 1. The critical observation here is that this 0 has a positive real part. So in the S-plane, the imaginary axis divides the left half plane and the right half plane. Any value of s which is with a positive real part lies in the right half plane. Any value of the negative real part also lies in the left half plane. So since our s is equals to positive 1, which is positive, it's definitely in the right plane. Okay, so this answers the first part of our problem statement. We have proven that right half plane 0 exists. And then I will discuss the poles and what this means for system stability. Thank you.
Okay, so thank you. I am Daniela Asare, and then I'm here to identify the system poles and analyze stability. So, poles of transfer function are found by setting the denominator equal to 0. So, in our denominator, we have into bracket s plus 1 times into bracket s plus 2. And then setting this equal to 0, we get to poles. That is s, which is equal, first of all, s will be equal to -1, and then s will be equal to -2, right? So both poles have negative real parts, which means that they are located on the left on the left side of the S plane. Yes. So now what does this tell us about the stability of the system? So for a linear time invariant system, right, to be stable, all the poles must be on the left half of the plane, right? So since both poles are found on the left, it's negative 2 and s equals to -2 and s equals to -1. They are found on the left side of the plane, of the S plane. That means that the system is stable. Yes. But however, we have certain classifications that we'll have to clear up. So although the system is like stable, right? The presence of the right half plane 0 is at s equal to +1. Yes, makes the system to be called a non-minimum phase system. Yes. So that's due to the fact that on the right plane, we have s equal to +1. Yes. It zeroes in at s equal to +1. Yeah. That makes the whole system a non-minimum phase system. So a minimum phase system has all their zeros and poles on the left half plane. But for what we have here, we have a little bit of a variation. Yes, we have our poles to be on the left hand side, and we have our zeros to be on the right half plane. Yes, sorry, we have our poles to be on the left half plane, and then we have um our zero to be on the right half plane. Yeah, so the non-minimum phase systems are stable, but they can exhibit unusual behavior, such as the inverse response, where the output initially moves in the opposite direction before settling. Yeah, so this is the whole analysis of the transfer function structure. So now I would hand it over to my colleague, Lucille, who will present on the step response. Thank you.
Hi, my name is Luso Abiti, and I'm here to take us through the unit step calculation of our assignment. So, the question asks us to find y of t with an input being a unit step signal. And we know that a unit step signal is a signal that is 0 for all negative values of t and 1 for all positive values of t. So we can express this mathematically as x of t being equal to u of t with a time range or a domain of t greater than or equal to 0. So to work with this, we have to convert it into Laplace transform because we are working in the frequency domain. So the Laplace transform of u of t will be equal to 1 over s. So we have our x of s to be equal to 1 over s. Earlier, we found that our h of s is equal to above, and we have our x of s now. So we can go ahead to find our output signal, which is y of s, which is equal to h of s times x of s. So substituting these into the equations, we have the overall transfer function of y of s being equal to 2 into bracket s minus 1 all over s plus 1 into bracket s plus 2 into brackets, all multiplying our unit step signal 1 on s. So multiplying this together, we have our output in the s domain. So to convert this back to the time domain, we have to find y of t. And we have to decompose this using partial fractions, which will be done subsequently. Thank you.
Thank you. My name is Panfo Joseph, and I'll begin with the partial fraction decomposition. So we have our fractions to be y of s is equal to 2s, 2 into bracket s minus 1, all on s into bracket s plus 1, then s plus 2. So we want to decompose this into simpler fraction in the form of y of s is equal to e over s plus b on s plus 1 and c on s plus 2, where we know that our e, our b, and c are all constants we are about to find. So we are going to use the cover-up method, and we'll find the distinct linear factors so that we'll be able to find our a, b, and c. The idea is to multiply both sides by the denominator factor, then you substitute values of s. That will make one part of the equation, that will make one part of them go to 0. So first, let's find e. So as you can see, let's multiply both sides by s. Then we set s is equal to 0. So if we set s is equal to 0, we are going to have a is equal to our 2 multiplying s minus 1 divided by s plus 1, then multiplying s plus 2. So you can evaluate with our normal mathematical terms. So you are going to get a to be negative 1. So that's our first coefficient. A is equal to negative 1. So for b, let's do the calculation also. So also b, we want to find a value of s that will make the factor 0. So we should take negative 1. So if you multiply both sides by the s plus 1, then we set s is equal to negative 1. We are getting b is equal to 2 into bracket s minus 1, all divided by s plus 2. Yeah, so when you put in the negative 1 here, upon doing our calculations, we get b is equal to 4. So we now have a to be negative 1 and b to be 4. Okay, I'll pass to my next colleague to help find the coefficients of the c part and also finalize the decomposition. Thank you.
Hi everybody, and thank you to the presenter 7 for handing over to me. I am called Peggy, and I'll find the last coefficient and complete the partial fraction expansion. So as shown on my screen, as a reminder, we are decomposing to s minus 1, s open bracket s plus 1, s plus 2, as it is equal to a over s plus b, open bracket s plus 1 plus c, open bracket s plus 2, close bracket. So as you found that a is equal to negative 1 and b is equal to 4, now we need c. Yeah, so using the cover-up method one more time, you have to multiply both sides by s plus 2, then set s, which is equal to negative 2, c, which is also equal to open bracket 2, open bracket s minus 1, close bracket, slash s, open bracket s plus 1, as shown on the screen, close bracket. It will be also evaluated as s is equal to minus 2c, which is also equal to 2, open bracket 2 plus 1, slash minus 2 and minus 1, multiplying minus 1, while c is equal to 2 minus 3 over the 2c, which is equal to minus 6 over the 2c, which is equal to 3, as shown on my screen. So c is equal to negative 3. So to summarize all the three coefficients, a is equal to negative 1, b is equal to 4, and c is also equal to negative 3. By substituting all these back into a partial fraction as we had before, fraction form, and the y of s, which is equal to negative 1 over s plus 4, open bracket s plus 1, close bracket, minus 3, open bracket s plus 2, close bracket, as shown on my screen. This is actually the complete partial fraction decomposition, of which these three terms has a simple, well-known inverse Laplace transform, which my member, who is a presenter 9, is about to also show or apply for us to get to the final domain answer. Thank you very much, and once again, I'm in the name of Peggy, and I'll hand over to my presenter 9. Thank you.
Thank you. My name is Hamzia, and I'll perform the conversion from the frequency domain to the time domain using the inverse Laplace transform. From the previous stage, we had our frequency domain solution to be y of s is equal to -1 on s plus 4 on s plus 1 minus 3 on s plus 2. We are going to apply the inverse Laplace transform to each of our individual terms. We know from our Laplace transform table that the inverse Laplace of 1 on s is simply 1. And since our first term is just -1 on s, we have the inverse Laplace to be -1. Now when we compare our second term to the inverse Laplace table, where 1 on s plus a is simply e to the power minus at, we see that the a here is just 1. So the inverse Laplace of this whole term is just 4 e to the power minus t. Similarly, the inverse Laplace transform of our third term would be minus 3 e to the power minus 2t. When we add these three terms, we get our final time response solution to be -1 plus 4 e to the power minus t minus 3 e to the power 2t, which is the complete time domain response of the system to a unit step input. I will explain what each of these terms mean physically. Now, for the -1, it represents the steady state value the output would approach as time goes to infinity. The exponential terms here represent the transient behavior that decays over time. And since both exponential terms have negative exponents, our earlier stability analysis is confirmed to be true. This is the complete solution to part 2 of the problem. And this is where I will end. Faith would give us a rundown of what we've spoken about so far. Thank you very much.
So thank you very much, Hamzia, and my name is Faida Kwamiao, and I'll be taking us through our complete solution and summarizing it. So first of all, we derive the transfer function from the parallel block. That is y of s over x of s is equal to 2 times s minus 1 all over s plus 1 times s plus 2. Then we identified the 0 at s, which is equal to 1, which is in the right half plane of our graph. This answered the first requirement of the problem. It proved that the right half plane zeros exist. Now, we found two poles at s is equal to -1 and s is equal to -2. Then we know that both of them are in the left-hand plane, confirming that our system is stable, because if our poles are found at the left-hand plane, then we have a stable system. Then fourthly, we classified this as a non-minimum phase system due to the right half plane zeros. This was a very important distinction because the system is stable, but it exhibits non-minimum phase characteristics. Finally, using inverse Laplace, we calculated the unit step response, and with that we got y of t is equal to -1 plus 4e to the power -t minus 3e to the power -2t. This answers the second requirement of obtaining y of t for our unit step inputs. So for the key takeaways, we were able to demonstrate a lot of control systems representations. So we were able to apply Laplace transforms, partial fractions in our solving of equations. We were able to derive transfer functions using our block diagram analysis. We were able to identify the poles and the zeros to show the physical significance in our graph. We were also able to We were also able to distinguish between stability and minimum phase behavior in our graphs. Thank you very much for your attention.